Listo, profesor.
Okay. And it's okay?
Yeah, let's start.
Okay, thank you. Thank you, Professor Mihail Croitoru, for accept the invitation. Today we are very pleasure to announce introduce the Professor Mihail. He talk for us invest Faraday's effect as a mechanism of optical control of quantum states in superconducting rings. Mihail has a large curriculum, and I have a brief resume here, and I read because I couldn't memorize, of course. Mihail Croitoru is a theoretical and computational physicist specializing in superconductivity, quantum transport, quantum dissipative, and no equilibrium phenomena in condensed matter systems. He received his PhD in physics from the University of Antwerp and has held research position across Europe, included at the University of Bordeaux, the University of Bayern, ASE University, and the University of Antwerp, as well as at Academia Cínica in Taiwan, and the professor position at the Federal University of Pernambuco in Brazil. His research combines analytical theory and advanced numerical modeling with interest spanning no equilibrium and dissipative process, correlated disorder, and quantum device physics. He has more than 100 papers, pre-review papers, publications, delivered many varied talks, and regularly serve as a referee from lead scientific journals. Mihail, you have 1 hour to your talk, and after this, missing 10 minutes, I will advise you. And after your talk, we go to question sections where all panelists can do a question for you and also the public, that because it is transmitted, it was be transmitted in YouTube. Okay, Mihail, go ahead.
Thank you very much for the nice introduction. So I will talk today about the inverse Faraday effect and its application to optical control of quantum states. These results, which I will present, originating from the work I did mostly in France and in Brazil. So let me start. So I will work with this computer. Okay, so first its outline. First I will make a brief overview of inverse Faraday effect. Then in its experimental realization in metals called atomic gases and possibly in superconductors. I will introduce theory behind which I used in order to simulate and predict some phenomena. Then I will show, based on that theory, how to manipulate current carrying states in superconducting rings. And then finally, I will touch some effects due to local defects. So, but first, before describing the inverse Faraday effect in superconductors, let me first revisit the fundamental phenomena of a direct or conventional Faraday effect, observed as a rotation of the polarization plane of light when transmitted through a magnetic medium. Specifically, is it visible? My screen is okay, visible? Yeah.
Yeah.
Yeah, okay. Just 1 second, I will check. Yeah. So the rotation angle denoted here as alpha f is influenced by parameters such as magnetization, m, refractive index n, a wave vector of light k, and the magneto-optical susceptibility He, which is a scalar value for isotropic media. A similar expression can be formulated in terms of Faraday constant, applied magnetic field B, and the effective travel distance of light within the medium. Okay. That was standard or conventional Faraday effect. Conventional Faraday effect has a reciprocal known as an inverse Faraday effect. Lev Pitaevsky predicted this phenomenon in 1961, and it was experimentally observed in 1965 by van der Ziel and co-authors, and they performed the experiment. The inverse Faraday effect is also an optomagnetic phenomenon. It manifests as induced magnetization, denoted as M, which aligns parallel or anti-parallel to the axis of circularly polarized excitation, depending on the helicity of radiation. The induced magnetization is directly proportional to the optical helicity, which is a vector product of electric field and its complex conjugate. Linearly polarized light does not induce any magnetization in the sample, as follows from this vector cross product. Thus, circularly polarized light excitation is equivalent to some extent to the action of the effective magnetic field. The phenomenon of inverse Faraday effect is a general feature of light-matter interaction. And basically, it should be observed across various media, including non-magnetic metallic systems and superconductors. The physics behind it is as follows. The instant electric field E of the circularly polarized light, incident normally to the metal surface, induces the excess of charge at the sample boundaries, which is dragged by the circular rotation of the field with velocity v or dv along the boundary. The spatial rotation of the electric field leads to an in-plane motion of the charge density along the sample boundary, creating, so basically like that, creating a non-zero time averaged edge current and consequently giving rise to a DC magnetization or DC magnetic moment. The Faraday constant, which is V here, which quantifies inverse Faraday effect, and it's basically a constant of proportionality between light intensity, which is this intensity of circularly polarized light, and induced magnetization, can be derived from off-diagonal conductivity tensor describing the Hall effect. To this point, I will come a bit later. So basically, there is a direct link between the inverse Faraday effect and the Hall effect. Now, what about current research status? So far, experimental evidence for the inverse Faraday effect in non-magnetic metals remains limited, with only a small number of reported studies. A recent palm probe experiment, reported 5 years ago, to some extent recent, reported optically induced magnetization in gold nanoparticles and also attributed to the inverse Faraday effect. The observed magnetization and demagnetization dynamics are ultra-fast, occurring on sub-picosecond timescales. These results support a picture of coherent angular momentum transfer from circularly polarized light to the conduction electron gas. So basically here I present from this paper the experimental setup people used in order to observe the inverse Faraday effect in gold nanoparticles. That was metallic nanoparticles, but what about Bose-Einstein condensate gases. It was also observed, for example, here, the persistent flow of Bose condensed atoms with a toroidal trap has been observed in works described in these papers, these two papers. A toroidal trap is formed by intersection of a sheet laser beam, red here, with Laguerre-Gauss tube beam, orange here. Quantized rotation is initiated by transferring 1 unit of the orbital angular momentum from Laguerre-Gauss photons to each atom within the trap. This process generates a current corresponding to a vortex of charge equal to the 1 orbital angular momentum. This picture shows, basically it's a snapshot, shows that observed flow persists within decay, of course it's decayed, for duration up to 120 seconds, so basically 2 minutes. It was possible to observe this rotation. But what about solid-state superconductors? In 2021, Buzdin and collaborators presented work demonstrating the emergence of inverse Faraday effect in standard superconductors. They found that in superconducting metals, two distinct inverse Faraday effect contributions are expected close to the critical temperature, the first one and the second one. The normal contribution from the normal quasi-particles and the contribution from the superconducting condensate. The physics behind normal electron contribution we have discussed already. But superfluid contribution requires broken particle-hole symmetry. Inhomogeneities, any homogeneities like boundaries, some other inhomogeneities, locally excite partially non-dissipative order parameter modes, which is in the system. And these modes coupled to the circularly polarized light via the gauge invariant vector potential A, generating a condensate response. So some few words about the physics behind. So it's on the next slide. They found in this paper that the second contribution of the inverse Faraday effect in superconductors is identified as a second-order nonlinear correction to the relation between the current and the vector potential. This second term is specific for superconductors only and reflects the concentration dependence. You see here, modification of the concentration of superfluid electrons, concentration dependence of superconducting gap function, and it arises solely from the dynamics of superconducting gap induced by circularly polarized light. But usually this term, so Q1, so kernel Q1 acquires such a big expression. In conventional superconductors is usually very small. Why it's small? That's on the next slide. So, as I said, it's small, but direct gap modulation, which basically induces the second contribution, or non-dissipative oscillatory contribution to the order parameter, is possible in non-conventional, or let's say in superconductors with non-negligible electron-hole asymmetry. This asymmetry arises from non-zero imaginary part of Ginzburg-Landau relaxation time. I would say, no, I didn't say correctly, it's opposite. Asymmetry is the origin for the non-zero imaginary part of Ginzburg-Landau relaxation time. And it's linked, as I said already, to the off-diagonal conducting tensor describing the Hall effect. So experimental observation of Hall effect in superconductors provide compelling evidence on the existence of inverse Faraday effect in superconductors. So a few words about this asymmetry. What is particle-Hall symmetry? Let's start from the dispersion relation shown in this figure. Physical process related to small perturbation in the ground state of the metal typically involves scattering of electron states in the vicinity of the Fermi energy, Phi. So in this particular case, this point, this line. Therefore, it's convenient to introduce the concept of quasi-particles. If energy of quasi-particles much smaller than Fermi energy. For ideal degenerate electron gas, one can define quasi-particle energy as shown here for the particles and for the holes. Standard expression. Note that according to the theory of the Fermi liquid, the spectrum of quasi-particle excitation in the strongly interacting isotropic system is identical to one of the ideal electron gas with the following expansion. So quasi-particle energy, it's a standard expression with plus for electron and for the holes. Okay. Let's look at this expression. The quasi-particle spectrum is symmetrical with respect to interchange between P and PF, if we neglect this term. However, it's becoming non-negligible if we're moving away from the Fermi level. So, effect of broken particle-Hall symmetry is well known in Hall effect, in the theory of the Hall effect. From the Drude theory, we have a non-diagonal component of the conductivity tensor only for the asymmetrical quasi-particle spectrum. Indeed, if we have a symmetrical one, this one will be 0. We have non-diagonal terms zero. If we have asymmetry, this term will become not 0, and then we have non-diagonal terms non-zero. We have a Hall effect, and consequently, we have an inverse Faraday effect. Okay. In S-wave superconductors, the quasi-particle spectrum is gapped, which leads to the mixing, due to this delta, of Hall-like and particle states at the Fermi level, or close to the Fermi level. As I said, for large energies, asymmetry between particle and Hall quasi-particle branches can be significant. And then we can linearize quasi-particle spectrum, and in order to obtain the useful expression for the density of states of electron in the close proximity to the Fermi energy. Since we are interested in superconductors only in the spectrum, in the close proximity within the Debye window, if we are dealing, for example, with phonon-assistant pairing. Then the density of states acquires the following form: the constant term, which is purely linear term, and the correction. Also, there are other corrections, but we will retain only the first one. The second term is usually neglected, and we deal with this one. But exactly the second term introduces the asymmetry in the spectrum. It naturally represents the particle Hall asymmetry, and it has the order of delta divided by Fermi energy. So that means this effect can be big, for example, for many band superconductors, for non-conventional superconductors. So basically in those systems where this fraction, this ratio is large. So basically, then substituting this full density of states in the derivation of the Ginzburg-Landau theory, so following Garikov or based on the quasi-classical description. Finally, here I nonlinear term I don't show here the linear term, so only non-linear term, only linear term, but for us most important the coefficient in front of the time derivative. So exactly this imaginary term is coming from this asymmetrical term in the density of states. Okay. Now, motivated basically by the above discussed experimental findings, which few of them I presented, we have performed a series of investigations of the generation of current carrying states due to the inverse Faraday effect. For that, we consider a system which consists of planar superconducting ring having radius r and width d and thickness much smaller, not r, but d and thickness much smaller than the superconducting coherence length. The ring is deposited on a thick, transparent substrate with a very large heat capacity and thermal conductivity to ensure a high cooling rate. This is the system we work with. This one. Next, we apply circularly polarized electromagnetic wave, and it's characterized by frequency omega and wave vector k, and it's incident perpendicular to the plane of the superconducting ring. The electric field for a circularly polarized radiation, sigma plus is for a right polarization, sigma minus is for left polarization, and is in the plane to the ring, and is given by this expression. The total vector potential A has only one angular component, which can be written in dimensions form as provided here. Okay. To address the problem of the evolution of the condensate in a ring, the ring is exposed to a circularly polarized electromagnetic radiation, and we solved the stochastic time-dependent Ginzburg-Landau equation of motion, which incorporates Langevin term, this one. Assuming a ring radius smaller than the length of the relaxation of electron-hole imbalance potential, we can eliminate from here. So basically it should be gauge invariant, but because electron-hole imbalance radius is much larger than the radius of the ring, we basically neglect that. Its contribution is negligible. Also, based on the above assumption, we introduce a complex relaxation time, this atom. As I said, just to repeat, this relaxation time accounts for a small imaginary part originating from electron-hole asymmetry. Okay. What else? Also, we neglect the contribution to the magnetic field coming from superconducting current, because screening is negligible in our system. This neglect is justified. Why is negligible? Because it's justified due to the fact that the cross-section of the sample is significantly smaller than the square of the London penetration depth. That's why we neglect it. Next, about the Langevin term. In the present model, the seeds for the condensate growth come from the thermal fluctuations. The influence of fluctuation effects on the macroscopic evolution of the order parameter is described in terms of this force zeta, with correlator given here. Correlator is Gaussian, that's why it's delta function, and the intensity of the noise, this intensity of the noise, is derived from the fluctuation dissipation theorem. And probably it's all about the setup. It's all about the setup, and now about the geometry. Considering the ring-shaped geometry described by the angle, so take into account the symmetry of the sample, we may write the order parameter as a spectral representation in terms of harmonics, so in other words, in terms of modes. So basically, we expand in Fourier, perform the Fourier expansion. We have only 1 degree of freedom. So basically, to some extent, it's a one-dimensional problem. Also, the spectral representation of the Langevin term we will also need in our equation. So all terms which is spatially dependent, we expand. And then the stochastic time-dependent Ginzburg-Landau equation transforms into a system of coupled differential equations governing the n modes of the order parameter. The stochastic time-dependent Ginzburg-Landau equation describing a single mode, a particular mode n, in the presence of for a moment without magnetic field, is exposed here. So this is nonlinear term, this is from Langevin term, and what the most important for us, this is little Parkes term, let's say, and for us important is the last two terms highlighted in green. So these terms reflect the contributions stemming from the circularly polarized electromagnetic wave. The first term, this one, and it's given, the full expression is given, facilitates the transfer of the optical angular momentum to the superconducting system. You see, from -1, n -1, and here we have n. Here n plus 1, and here we have n. N plus 2, and here we have n minus 2, and here. So basically it's a kernel for transferring the angular momentum. Next term, the subsequent term, solely induces laser-induced heating. As one can see from this expression, it plays the role of increase of temperature, and when this term is large, then larger than, for example, a certain threshold, the effective temperature of the system exceeds critical temperature, and superconductivity may start nucleation only when the radiation is switched off. Okay. First, let me talk about analytical solution of this problem. In the limit of weak wave amplitude, weak meaning that amplitude parameter, and by amplitude parameter I call E divided by frequency, is smaller than the reduced temperature. Smaller than the reduced temperature. Reduced temperature is simply 1 minus T divided by Tc0. It's standard reduced temperature in superconductivity. And considering temperature close to Tc, so not so far from Tc, we can find the analytical solution of the stochastic time-dependent Ginzburg-Landau equation by perturbative approach. For that, we introduce dimensionless parameters. So basically, it's R, sample size, reduced temperature, this vector potential, and then in this here should be small a, and then in this dimensional standard expression for the dimensional current, and now the solution. In the first order approximation with respect to the amplitude E, oh, this amplitude, the radiation generates only AC, alternating current, which does not depend on the imaginary part of the relaxation constant. That means if we switch the current, basically there is no DC, there is no persistent current. So in the first approximation, we induce only alternating current, no persistent current, no DC current. That means we need to go to the next step, next perturbation, next level of perturbation. In the second order of perturbation, we can find the constant or persistent or DC contribution to the current, and it's correspond to the inverse Faraday effect. This figure shows the stationary current generated in the ring as a function of frequency of the radiation with constant amplitude. So current as a function of the frequency. Dashed curve is obtained from the analytical expression, so basically from perturbation approach, while the red curve represents the result of numerical calculations performed with a number of expansion in the Fourier expansion. Basically, we keep only 17 harmonics, 17 modes within these approximations. I would say that for the system we consider a contribution already of modes with index larger than 4, it's negligible. But to be sure, we keep 8. So what we see, what one can see from this result, for a given set of parameters, both approaches give similar result when the radiation frequency is larger than 1. Larger than 1, basically, starting from this, larger than 1. However, it shows marked discrepancies for lower frequencies. That is, when effective amplitude ratio E divided by omega, so basically E divided by omega becomes large. So we work, our small parameter is amplitude parameter E divided by omega. When omega is large, since it's in the denominator, this parameter becomes large. That's why for that case, a perturbative approach does not show correct result. Yeah. Now that was theoretical perturbative solution, but now let's see results applicable for light operated current carrying state. So what we need to explore the possibility of triggering a switch between different current carrying state using circularly polarized light or radiation. we analyze the emergence of superconductivity when the radiation amplitude gradually decreases to zero in the presence of the half-quantum magnetic flux. So setup is a bit different from setup I used to solve the problem analytically. So I add a half flux quantum to the system on the top of circular polarized light, and then initially system, and basically I evolve the system for time larger than zero. And for that time, I apply external illumination. Basically, I would say that at time equal to zero, system is in the normal metallic state. Superconductivity was destroyed by strong illumination, and then illumination is switched off and amplitude decays exponentially. The characteristic time decay is tau e. The sample setup is shown here. This is substrate, this is our ring. Arrows pointing up is a DC magnetic field. Yellow is illumination, and the current is shown in yellow, the current we are looking for. Okay. So for that, we need to solve numerically system of coupled time-dependent Ginzburg-Landau equations, stochastic time-dependent Ginzburg-Landau equations in the presence of external magnetic field. So if compare with the previous situation, I add here magnetic field, highlighted in red, and I'm looking for the current. Current in the mode representation takes the form shown here. Few words about the physical situation we deal here with. So, as follows from the theory of little parks, why basically we need half flux quantum. And it's related to the little parks theory. So from that theory, the critical temperature of superconducting ring is a periodic function of magnetic flux through the ring with a period equal to the flux quantum. So basically, critical temperature follows this curve. Exactly at half flux quantum, the ground state of the ring becomes degenerate. Yes, so we have n equal to 1 and n equal to 0. So it's degenerate at this point. The ring may be in one of the two superconducting states, either n equal to 0 or n equal to 1 with opposite current direction. So n equal to 0 in this situation is counterclockwise, n equal to 1 is clockwise. These states are separated by free energy barrier, and a small deviation of the flux from half quantum should not actually cause a transition between them. Okay. So as indicated, two states, n equal to 0 and n equal to 1, are degenerate, separated by free energy barrier. And starting from the high intensity illumination, as I already indicated there, so we start from the normal metallic state. Superconductivity is destroyed. And then we subsequently decrease the light intensity. And the presence of light intensity will leave degeneracy by inverse Faraday effect. And one can expect a realization of current carrying states controlled by radiation pulse. yeah, this is original expectation. Okay, here are the results. Here the probability of the final stationary state as a function of decaying time is shown. So it's probability, characteristic time of the decay. Clearly, the final superconducting state is determined by the helicity of radiation. Look, here it's counterclockwise, here clockwise. So here in the right panel we use one polarization, and in left another polarization. So superconducting state is determined by helicity of radiation. And we see almost 100% probability for slow switching times. So here, when switching time is fast, probability is rather small, but it approaches 100% for slow switching times. Sigma plus radiation generates counterclock current, sigma minus clockwise current. So this result shows that circularly polarized radiation can be used as an effective magnetic field for switching between different current carrying state of a superconducting ring. Actually, we can go to the shorter decay times, but in this case, system will generate a non-adiabatic superconductivity, a regime with strong fluctuations that affect the entire spectrum. And this is what we see here. So if we go to the short decay time, of course, we cannot apply any more Ginzburg-Landau. One has to deal with time-dependent Eilenberger equation or time-dependent Bogoliubov-Desjardins equation. But we see already, but for the purpose of generating or controlling the current carrying state, we see already a tendency towards non-deterministic probability. So non-deterministic switching. So it will become probabilistic switching, and this is what we don't want for engineering application, let's say. We can go, yeah. Okay. Next result. Here, we investigate the dependence of probability of realizing the final state on frequency. So probability is a function of frequency. For counterclockwise polarization, the imbalance between probability for n equal to 0 for 0 mode and for n equal to 1 mode quickly reaches unity at small frequencies and remain relatively constant up to omega approximately 0.7 here. Afterwards, it starts to decrease monotonically at high frequencies. So here I show only one polarization, because for another polarization, simply it will be a switch between these two curves. Red will be here, green will stay here. Next, we need to demonstrate the sensitivity of switching effect to the external flux fluctuations. And here I present the influence of amplitude of the applied DC magnetic field or DC magnetic flux and how it influences on the probability. It's clear that probability of reaching the desired final state is already close to unity when the flux larger than, let's say, 0.42, 45. In case this was obtained for the decay, here it should be 0 point. For the decay 50, for the 15, yes, for 15. Basically, numerical calculations show that 100% switching effect can be achieved at even lower magnetic field, not at 0.45, but even at lower. But for that, one need to increase switch off times of the illumination pulse. Okay. Yeah. Now I turn to analyze the role of sample size and the probability of switching effect. 15 minutes left. Here, figure displays how the radius of ring affects the probabilities of realizing the stationary states 0 mode and 1 mode for the counterclockwise polarization. One clearly sees that rings with small radius achieve deterministic current carrying states at low frequency amplitudes. And at a low, And from this figure, one can conclude that reducing the size of the system strongly promotes the holistic control switching. For example, this one was obtained for radius 4.5 in units of coherence length, and this one was obtained for 9.4.5 in coherence length. So basically, decreasing the size increases the switching ability of the system. Okay, now, so far we have seen that presence of circularly polarized radiation discriminates between two superconducting states, enabling holistic control state generation. And we modeled the system. We used setup where initially system was in normal state. But in engineering application, we usually have something like in a computer, we have 0, 1. We need to switch from one state to another one. So let's see if it will work in this situation. So let's investigate the regime where the system initially was in superconducting state, but for example, in n equal 0, so in n in 0 mode. And for that, we already consider Gaussian pulse, again with the switching of time tau e. The maximum pulse amplitude is high enough in order to destroy superconductivity. Yeah, here, these figures show the temporal evolution of the order parameter harmonics. So you see here a few harmonics from 0 to 4. Of course, I used from -8 to +8, all harmonics was in the numerical simulation, but in order to show here on the figure, I present only from 0 to 4, from 0 to -4. We see that a radiation pulse initially excites multiple harmonics. However, only a single harmonic survives after the pulse. Characteristic relaxation time to reach equilibrium after the pulse is of the order of 2 pulses. So pulses of this size, and then superconductivity start to grow, something like after another decay time. Simulations this is for particular noise realization, but in simulation, in order to obtain the probability, 500 noise realization was used, which enabled to extract the probability distribution of a final state. This figure presents the probability of generating final state +1 as a function of radiation frequency at different radiation amplitude, ranging from 1.5 to 5. So red corresponds to 1.5, brown to 5. The external radiation pulse was approximately 10 in Ginzburg-Landau time. Sigma minus polarization, it's for the left panel, sigma plus polarization for the right panel. One can clearly see that sigma minus radiation with intensity larger than 1.5 induces 100% switching at low frequency, increasing omega to a maximum, and this maximum depends on intensity, leads to a drop of intensity, of switching off probability. And then probability for extremely large frequencies approaches 50%, which is useless for engineering application. We see this maximum threshold decreases as we increase the amplitude. So again, it's evident from this data that altering the Kill reality of the radiation enables complete transfer of the ring from one current carrying state to another. So either we move it to state 1 or we move to state 0, the system. Here I show, so basically numerical, so far we have neglected the heating effect caused by radiation and assume the temperature of the ring to be constant. If we will take into account also the heating effect, of course, this will influence the result, but for example, these calculations have been done for the case when initial laser increase the temperature of the system to 1.2 from critical temperature. That means 1.2 critical temperatures. And we assume that thermal conductivity may not be high enough to quickly dissipate the heat into the substrate, that therefore it may be necessary to take into account the heating effect. So heating effect slightly decrease the switching effect, but notably, even at significantly large radiation amplitude, the switching mechanism remains almost unaffected to some extent, I would say. Yeah, approximately 100% for the case of when we deal with amplitude equal to 5. Next, I'm going to talk about the effect influence of defects. So I have still 6 minutes. Let me.
Excuse me, Mihail.
Yeah.
You have 10 minutes more.
10 minutes. Okay. Yeah. Let's investigate effect of inhomogeneities. Local temperature inhomogeneities may arise from non-uniform thermal coupling, for example, to the substrate, or from material defects within the ring. To account for such effects, we consider a scenario in which a small region of ring, so here, small region of ring, is characterized by a local temperature T local, which may be higher or lower than the temperature of the rest of the ring. The region with modified temperature is assumed to be much smaller than superconducting coherence length. In this situation, the setup can be equivalently described as a localized delta function variation of the critical temperature. So our results apply to the system with uniform temperature, but featuring a local variation of critical temperature, or opposite to the uniform critical temperature and local variation of ring temperature. The first one can originate, for example, from the fluctuations of ring parameters of local defects. The second one is from, for example, a bad contact at some certain point of the ring between the ring and the substrate. Again, For that, we again employ the stochastic time-dependent Ginzburg-Landau equation. The local temperature variation is incorporated already through the first term of the ring. So it's here, this local temperature variation. And then, following the same procedure, we obtain a system of coupled differential equations for n Fourier modes of the order parameter. As usual, stochastic time-dependent Ginzburg-Landau equation for the nth mode, including the effect of external magnetic field, is written here. The term accounting for the defect is this one, is highlighted in red. In this framework, gamma larger than 0 correspond to a local increase of the temperature, which is equivalent to a local decrease of superconducting transition temperature. And gamma smaller than 0 correspond to the opposite situation. Okay, now a few words about the physics in order to explain the result. So let us investigate what local defect does. For that, it's useful to deal with free energy of the system. As we discussed already, without circularly polarized radiation, the winding number states n equal to 0, n equal to 1 are degenerate and stable in the absence of defect. The superconducting transition temperature of the ring is smaller than its bulk counterpart. It's standard because we deal with a ring, so critical temperature is slightly small. The two states are separated by free energy barrier, this free energy barrier, and when we do not have any defects, so we work in this, we follow this line, zero line, and we see that barrier increases upon cooling. So increasing cooling increases barrier. But local defect changes the barrier height. So either we go to the right or to the left, we change the barrier height. So figures show the free energy barrier versus defect strength for several temperatures. And the mathematical expression for the barrier are given here in dimensional units. Above a critical value, some critical value, which depends on the reduced temperature, we do not have barrier. For example, above, for a certain value of defect, we do not have barrier. And this temperature, branching temperature, I will call it, depend on the defect strength. Okay. For specific defect strength, the barrier vanishes, as I said. And this leads to a strong mixing of zero harmonic and one harmonic. Since we do not have any barrier between them in free energy, so they start to mix. Specifically, this result, for example, this is branching point temperature, branching temperature. Specifically, this results for positive defect above this branching point when barrier disappeared, has vanished, Psi0 is equal to minus Psi1. Amplitudes are equal, phases are different. In negative case, they're exactly equal. So if they're exactly equal, due to potential barrier vanishing, these mixed states do not carry any current. So we do not have any current. So if we work here, switching effect is 0. But at low temperatures, the barrier reappears and the mixed state becomes unstable, yielding ground state either predominantly with 0 mode or predominantly with first mode. And the ring exhibits the current either in one direction or in another direction. And these are results. Here we track, again, this is modes of the order parameter. So we track here dynamical evolution of the order parameter as a function of time for a single noise realization. And for gamma equal here minus 0,1 and here plus 0. In case of negative, in case of cold point, cold defect, critical temperature is smaller from branching point and the mixed state is not realized, and the system relaxes into a current carrying state dominated by a single harmonics. In this particular case, and by red harmonics, red is 0. So there is a current. Because they are not equal, the current will flow in counterclockwise direction. In case of positive defect, temperature is larger. I didn't show here, but temperature is larger than branching point, and the mixed state is realized. And you see it's here. The curves are merged, but you see the green one on the top of red one here. So they're exactly equal. If they exactly equal, the current, I mean, the contribution of the next one is negligible, the current is 0. So we need, in order to still use the switching effect of the inverse Faraday effect, we need to keep temperature below the branching temperature. If we do that, then we obtain the following result. Again, as I said, we are interested in the effect of switching between two different current states. Yeah. So left figure displays the switching effect for a clean sample. The right one for a ring with a defect. The switching occurs in the ring sample approximately for amplitude 0.2, for right panel for 0.15. So we see that defect reduces the switching threshold by approximately 25%. So physical mechanism behind that. So near the branching point, as I showed in the previous slides, the free energy landscape softens. The barrier between two current carrying regimes is reduced. And therefore, a smaller inverse Faraday-induced effective amplitude, or let's call it effective bias, is sufficient for deterministic switching. And now I'm coming to the conclusions. Yeah. Here I simply again show an inverse Faraday effect, which offers the ability to deterministically optically switch between different current carrying states in superconducting nanorings. That was the model. In reality, one can use a system of rings. So a suitable system for observing the predicted effect can be an array of small superconducting rings in magnetic field that creates half flux quantum through the ring. And then one can use nanosquid to determine the direction of the current. And finally, I'm coming to the conclusions. So what we did, we demonstrated that complete and efficient switching between different current carrying states and superconducting nanoring can be achieved by utilizing the helicity of external radiation. And I showed that localized defect to some extent enhances the inverse Faraday effect in superconducting rings at half quantum. So basically combining defect engineering and operation close to the branching temperature allows low power, optically controlled manipulation of persistent currents. Thank you. Thank you for your attention.
Thank you, Mihail. Thank you very much for your very interesting talk. And and now we have a session of questions, and I will be the first one. Sorry.
Yeah.
You talk that you have used the half magnetic flux to can and what you can achieve use electricity, etc., etc. But you show that the half magnetic flux is not a minimum in energy; it's a metastable. Just on in your last three. Okay, so you can explain your theory, but the transition is from metastable to metastable. Only this way you can imagine the half magnetic flux. But my question is, how can active the half magnetic flux, for example, in the lab?
You mean how to achieve half magnetic flux quantum?
Yeah, because
But
the
taking the geometry of the sample and taking, I understand that you mean that we have a rather small ring of the order of, let's say, 5, 10 C, that means coherence length. It's quite small, but let's say diamond-based or magnetic field determinators or squids allowed to tune very precisely magnetic field. So I don't think it's a problem to tune half quantum exactly to the point. And on the top of that, that's why I investigated the stability of the results with respect to deviation from half quantum. And I showed that, for example, 0.45 flux is also gives rise to switching effect.
okay, thank you. I will invite others panelists to do his questions. Mauro Doria, can you?
Hi, Misha. Nice to
Hello, Mauro.
talk and nice to see you again.
Nice to see you.
First question. I mean, the inverse Faraday effect, I mean, I have not been in contact with the literature, but it has been used a lot to determine current carrying states at the surface, at least, no? I mean, in many situations. So I felt that you were kind of developing this, perhaps having in mind quantum computing, no?
Yes,
I mean,
yes.
yeah, entrance of half fluxes. But I mean, what about other situations? I mean, your theory, for instance, for determination of well, Hall effect and so forth. Has this been used, the inverse Faraday effect?
So regarding the experiments.
Yes.
So first, inverse Faraday effect, it's a long time known effect in the field of magnetism. So it's from 1965, it's used. But so far, let's say till 2020, and only in 2020,
Entra aqui, por favor.
only in
Pode vir aqui um instantinho, não?
Oi?
Pode vir aqui um instantinho?
Entra.
Não, o senhor pode vir aqui um instantinho, rapidinho?
Só um minutinho.
So it was reported the first experiment where the authors manage to observe inverse Faraday effect in normal metal. So they found induced magnetization in a standard metal, in that particular case in gold nanoparticles. Before that, it was possible only to induce magnetization with externally with external circularly polarized light only in magnetic materials, where already magnetic moment is present, and then external light allowed only to tune that magnetic moment to a certain direction. In metal, it was for the first time, has been done only in 2020. In cold atomic gases, a bit earlier, in 2015, and in superconductors. So far, there is no experiment that unambiguously show the inverse Faraday effect in standard, even non-conventional superconductors. Currently, a group in Optical Institute in Bordeaux, led by Brahim Luni, they try to do that. Also, Vladimir Krasnov in University of Stockholm, they try to do that, but so far there is no experimental evidence. But taking into account that inverse Faraday effect is directly linked to a Hall effect, and Hall effect was observed in superconductors, that means that it's a matter of time only, and sooner or later it will be proved that it will be observed inverse Faraday effect in superconductors. But in metals, for the first time, it was observed only 5 years ago.
So, one last thing,
Yep.
I think we have a proposal for you about observing the inverse Faraday effect in type 1 superconductor. But I talk to you later on about that, because time is already late. Thank you very much for your lecture.
Thank you, Mauro, for your question.
Thank you, Mauro.
And let me, Gabriela, do you have a question?
Hello, Mihail. Thank you very much for your talk. It's very interesting, the subject. I wanted to address some stuff. You about the conclusions. You this kind of calculations or this theory is already are things already measured, and this use about memory superconducting controlled by this optical polarized light.
Okay.
That
Yeah. Please go ahead. Okay, as I said, two groups, one in Institute of Optics in the University of Bordeaux, CNRS Bordeaux, they tried to make that, but so far there is a problem with samples. There is another group in the University of Stockholm. They have good samples, but it seems to me they have another problem with tuning and setting up everything properly. But so far they try to measure, and I expect, basically we expected that to have result in 2023, but for a moment not. A group from University of Prague also wanted to join, but I don't know how they evolve in the constructing their setup. Regarding the quantum computing, what I said here, basically we need to what I said here, it was a classical world. Next, we need to quantize in order to move to a two-level system. What I presented here, it's basically it's a potential energy part of the Hamiltonian. In order to obtain kinetic part, we need to go beyond this theory, and as I said at the very beginning, we assume that we neglect the scalar potential due to the fact that electron hole distance L is larger than our sample. In order to obtain properly kinetic term, we need to take that into account, and that sufficiently increases calculation time. When we will do that, we will be able to quantize also the kinetic part, and then having quantized potential part and kinetic part, we will move everything to a two-level system, and then we can already deal in this system in the way similar to standard quantum computers based on Josephson junctions. But for a moment, as I said, for the theory, we need to go beyond the current presentation and to include scalar potential, and then we will construct the theory. And next step is already wait for what will be the result from efforts of experimentalists.
Okay, yes. And about this defect possibilities, the defect can make you tune, and that's something you are already calculating. But I guess
Yes.
also
Yes.
go experiments will be very, very difficult.
Yes.
Yes.
Defect does not create any sufficient problems in calculations. So that's why I presented here, and simply it softens the free energy barrier between 0 and 1 mode, and that allows to speed up the switch between 0 and 1 mode. Basically, if we have quite slow switching, then we simply include and basically engineer the system by including the defect there, and then switching time will increase, as I showed in one of the last slides.
Right. But of course, probably the experiments will be much more difficult.
Yeah.
These codes you are using to calculate are made by your group.
It's everything was done in the group of Buzdin. So basically, yeah, I'm collaborating that group with that group, and I'm doing them. And that group is related to the group of Institute of Optics by Brahim Louni, where they try to do that experimentally. Also in the University of Bordeaux.
Right. Thank you very much. Very interesting. Very interesting stuff.
Thank you. Thank you for the question.
Thank you, Gabriela. And the next question will be done by Professor Stewart from London College.
Yeah. Mm-hmm.
Mihail, thank you for your fascinating talk. Very, very interesting. I understood a small fraction of it, so I'm going to ask some practical, more practical questions. Did I understand correctly that the superconducting properties of the ring are only important if you have a defect or an imperfect ring? Did I understand that correctly?
No. So basically, originally, we investigated the switching effect in a clean sample. And then appeared a question, because defects are unavoidable in the system, especially in such small system. So we start to investigate the influence of defects. And then appeared some bistable system. In one situation, effect is totally destroyed, switching, not the current, because here two effects were interesting. We are interested in. One is switching for the quantum computer, and another one is simply linear response. Linear response is perfectly working, but switching basically was killed. And then we started to investigate and realized that barrier between these two states disappears after a certain threshold, as I said, branching point. And then one has to deal with two situations. Either we work very close to TC, And that's not so interesting because very close to TC we have a lot of fluctuations, and exactly at that region we have a destruction of switching effect. But if we go below the branching point, let's say it's depend on the strength of the defect. It can be 0.8, it can be 0.9, so it's quite deep inside the superconducting state region. Then the switching is recovered again, and moreover, it's provided us with some advantages, and one of them, the switching time increases. So basically, in any situation, switching, if we below the branching point, switching is present. But on another side, what we thought that originally the defect is antagonistic to the effect, finally led to the conclusion it's not the case if we are below the branching point, but opposite. It preserves the switching effect, but even decreases the switching time, the let's say response time for switching effect.
Just one further comment with the into the quantum realm, the Josephson junction qubit has the problem that it's not really scalable. So scalability is seen as a really positive property. So
yeah.
The effects of as you go to smaller dimensions, the effects of defects and so on will have to be fully understood in the way that you just described. Sorry, that was more a comment than a question.
Yeah.
But thank you for your presentation. Very interesting. Thank you. I learned a lot today. Thank you.
Thank you for the question.
Thank you, Stuart. The next is Alexander. Alexander?
Oh. Thank you very much, Professor Mihail, for the talk. It was really interesting. I had several questions that were already addressed by the previous panelists, but in particular, I had the question about the physical implications of the presence of this free energy barrier that you mentioned before.
Yeah.
If you can add something about that, what is the physical implication of this barrier and when it's important?
You see, as I explained during the talk, so in order to deal with the system, it's better to work with the free energy. In the free energy landscape, we have T valleys, let's say one of n equal to 0, one is n equal to 1. And this is for the case when we have half quantum, positive half flux quantum. If, for example, we have free half, of course, we will have to deal with valleys 1 and 2 and so on. So in any case, we are on the point between two neighboring valleys, depending on the flux. And but this picture is related, basically it's critical temperature, how it behaves. And then if we have already two valleys and the barrier between them, so then system somewhere on the top of this hill, on the top of this king, then with the external laser we can either push system either to one valley or to another valley, and then the barrier preserves the state from moving from one side to another one, for example, due to fluctuation. So I would say from one side, it's better to have higher free energy barrier. In this case, of course, there is less probability, let's say the system is more robust. Less probability for a system occasionally to move from one side. We, for example, submitted a counterclockwise elimination and obtained counterclockwise clockwise current. And we don't want to obtain counterclockwise current. So it may happen due to some fluctuations. So these fluctuations are strongly reduced with the increase of the barrier between these two states. But from another side, as higher as this barrier is, as longer time we need to perform the switching, especially taking into account the engineering application of this effect. But if we will go to a very small barrier, let's say we are approaching very closely to the branching point, the switching time decreases, but from another side, fluctuations can be quite large, and we have to deal with that, and we don't want fluctuations in the protocol we are interested in. So here should be a compromise depending on the system or application of the system. If we want, for example, let's say, very robust system, like in experiment, we can go far away from the branching point, meaning that we, let's say, either decrease temperature or decrease the defect strength of the defect, but it will be more difficult in the experiment. So far in defect engineering, it's not so advanced. So we simply go down in temperature, we cool down the system. If we're interested very much in the switching time, opposite, we increase the strength or we increase the temperature. And then we, of course, admit fluctuations, protocol, and then we need to include corrections in the system. But on another side, frequency of switching is high. So it depends on the application.
Okay, thank you very much. Another question is about the defects that you already mentioned before. You only put defects on the temperature, but maybe you can also have in a real sample other types of defects. I don't know if you can mention the importance of the defects in general, because I thought that when you change the temperatures, it can have some advance to have the defect, etc. But maybe with other kind of defects, maybe the situation is different. I don't know if you can mention something about that.
You mean we studied inhomogeneities and temperature around the ring?
Yes, but you can also have other type of defects.
Yeah, as I said in the model, so you see, the model is quite general because it allows two situations. Either we have a homogeneous temperature and fluctuating critical temperature, or we have a homogeneous critical temperature and fluctuating system temperature. Let's consider both situations. So we have a homogeneous critical temperature. That means our ring is homogeneous, and we have a fluctuating system temperature. What means fluctuating system temperature? That means some connection at some point. So ring is on the top of the substrate. Some points of this connection can have a good connection, some bad connection. That means sink or decrease or transferring of temperature or heat to the substrate in some situations at some point can be large, in some small. That means some points of the ring will become hot, some points of the ring will become hot. This situation which I described. But exactly this, so it's basically there is a symmetry. Either we consider TC constant and T fluctuating, or we consider T constant, TC fluctuating. Second situation, T is constant and TC fluctuating. If TC is fluctuating, that means parameters of the system are different. That means somewhere there is a real add atom. This add atom or twinning plane or twinning point, let's say, because we have a ring twinning point, and this twinning point will increase critical temperature, even though the system temperature is correct, the constant is constant. So both situations, either fluctuation of temperature or adding real disorder, but as I said, we consider only one defect, are let's incorporated in the theory. So both situations are incorporated. And in both situations, the result will be the same as I presented. But as I said, in order to include next step, of course, will be to include random defects with correlation or without correlation, but it's already second question, and to study what will happen then. But here one have to take into account, if we have many defects, let's say we have a disorder, and the strength of the disorder is not strong, then we can renormalize our parameters like coherence length, London penetration depth, and the rest, and let's say inhomogeneate the system. Only important is to go to very strong disorder. But when it will be very strong disorder, then we can kill superconductivity at all. So in this situation, the ring can be divided, let's say, in superconducting grains interconnected with insulating parts. So it's not interesting for the application.
Okay. Thank you very much again. Very nice talk. Thank you.
Thank you. Thank you.
Thank you, Alexander. Now the question will be done by Professor Augusto Moreira. Augusto.
Mm-hmm.
Nice presentation. It's not
Thank
my area, but the question is very simple. Sometimes bilayer graphene under certain magic angles behave like a superconductor, and this kind of formalism, all the mathematics that you presentation here can be used for this system. It's a curious. This is the question. It's a simple one. Thanks.
Mm-hmm. Magic angles in graphene. Honestly speaking, I never worked with that, so it's difficult. Probably it will appear second degree of freedom. That means so it will not be a quasi one-dimensional system. We'll have to take a two-dimensional, the second dimension into account in order to account this, as I can imagine, these magic angles. So from this perspective, calculations will be much more difficult. But from the point of view, if it's prohibitive or not, I would say not. So it's possible to calculate. The point is, what is the critical temperature in the graphene, in the graphene in this case, and how that critical temperature is related to disorder from one side, but from another side, one can take into account that graphene can be quite clean. So my immediate answer could be that one can calculate, but immediate obstacle is I would say one has to deal. I would say in this situation, it's better to solve directly Ginzburg-Landau without decomposing in spectrum. So basically, you need finite difference scheme, and in this situation, it will be much faster. Because in our calculations, I use I use a lot the symmetry of the system, and in the setup you propose symmetry is lower, so that means one has to calculate directly time-dependent Ginzburg-Landau within the finite element or finite difference scheme. But for the rest, time-dependent Ginzburg-Landau theory is a general theory of phase transition, so it's applicable to everywhere. Within the space, of course, within the limited range close to the transition temperature.
Okay, thanks for the answer.
Well, thank you, Augusto. Now from National University of Colombia, Professora Ximena.
Thank you, Professor Isaías. It was an interesting talk. I don't have a question about it. I only say thank you for incredible talk. And we don't have any question from our network, but the people only say thank you for your talk. And the people say that it is an interesting topic. Thank you.
Thank you very much.
Thank you, Ximena. Daniel, are you here?
Hi, Saya. Good morning.
Morning.
Nice talk, Professor. I don't have question because I really am more or less late because I was very busy here at home. So, but is the last part I like it very much. So that's it. Thank you.
Oh, thank you,
Thank
Daniel. Now, Andrea, do you have a question?
Hi. Yes. Thank you, Professor Isaías. First of all, congratulations, Professor Croitoru. I would like to understand whether the model is applied to the thin ring.
I'm sorry?
Sorry, my camera. Okay. I would like to understand whether the model is applied to the thin rings lying on a sapphire plane, or if it represents a cross-section of a very long cylinder. And second, I am also curious about which software you use to create the illustration on the page 46 and 47.
46 and 47.
The software, only the software.
This one. And this one. It was written by my co-author, Sergei Mironov. He made it using AutoCAD. You mean 46 and 40? This one and this one was done within in the AutoCAD software. But the first part, in order to answer, could you please repeat? I couldn't understand the question.
Yeah, the question is the model is applied in the thin ring?
Applicable to what?
Cross section the very long cylinder.
No, it's a ring, and this is simply illuminate. It's let's say strays of illumination. It's illumination. It's a light, and this one is simply in order to somehow to show, it's a sketch of the circular polarized light. But superconducting sample is this one, this ring.
Okay, thank you
This
very
is the-
much.
Okay, thank you, Andrea. I could realize your question. I know why. Okay, I don't know if everybody have done the questions. Any more person would you like to do other questions? If not, if possible, Mihail, you can
Yep.
turn off your presentation.
Turn off presentation, yeah.
Yeah. Thank you. And so, if possible, everybody can open our camera to thanks again the speaker. But before thank the speaker, Mihail, do you have any other final comments?
No. I simply want to say that thank you for many questions, thank you for the interest in this talk and interest in this topic. And I'm happy to be here again. And honestly speaking, also I would like to send my regards to Albino. It was a nice time when I've been in University of Pernambuco. I worked with him. Unfortunately, he is not present here and was not present 2 weeks ago. I hope to meet him again and to simply, if one meet him, simply take my regards to him.
Okay. Thank you, Mihail, one more time, and everybody. James, when
Thank you.
would like finish it, can
Thank you.
Thank you
Thank
very
you very
much,
much.
Misha.
Thank you very
Bye-bye.
much. Thank you very
Very
much.
okay for everybody.
Have a good day.
Bye.